Thermal analysis is an integral part of electronic design. You don't just want the circuit to simply work, you also need it to function for long periods of time in a reliable fashion. One key element to this is preventing overheating. So hello and welcome back. Today I want to look at thermal models and how these can be implemented in a circuit simulator. I will be starting with the basic steady state models and slowly work up through the transient thermal models and finally look at the all-in-one electrothermal models. So if you're curious, then keep watching. So let's start simple. The electrical equivalent steady-state thermal model that can be either calculated by hand or simulated when it's a bit more complex requires three main building blocks: a voltage source that represents the ambient temperature, a current source that represents the dissipated power, and a thermal resistance that represents how difficult it is for the power to get from the heat source to the ambient. With this model, the temperature is represented by the voltage in the circuit, so the voltage on the voltage source is obviously known, it's the ambient temperature that we've just set, but the quantity that we wish to figure out, the temperature on the heat source, will be the voltage present on the current source. The higher the thermal resistance, the higher the junction temperature will be. While extremely simple, this sort of model can be used to predict the behavior of quite complex systems. So, for example, let's say we have two heat sources, two transistors, dissipating different amounts of heat, but placed on the same heatsink. While you usually want separated heatsinks, this sort of arrangement might be necessary for space saving or other reasons. So the question is, how hot does this thing get? Well, an equivalent circuit for this can be built as such. So on the left side, I started with the power dissipating junctions, the current sources, I set these both to be 2 watts, and on the far right side, I set the ambient temperature, so a voltage source set to 25 degrees Celsius. Now, the heat will go from one side to the other through multiple paths. On the two inner lanes, I set the junction to case thermal resistances, and then I also added the thermal interfaces, so things like thermal paste and isolators. Now, these both come together on the heatsink, and from this point, we go to the ambient temperature through the heatsink's thermal resistance. Now, other than this, another less efficient way of dissipation, but still not completely to be disconsidered, is the heat transfer from the transistor's case directly to the ambient. So usually, here we have some very large junction to ambient thermal resistances, so that's why this path is commonly neglected. Anyway, if we run the simulation, so I just made a basic operating point simulation, we can observe the exact temperatures in each of the circuit nodes. So the ambient is at 25, as we've set it. Then we can see that the heatsink is at a higher temperature, so about 37 degrees. The transistor cases are even hotter than this, 39 and 38. And finally, the two junctions are at the highest values, so 44 and 41. So in this specific case, there's absolutely no risk of damage, but there still is a non-neglectable temperature difference in between the two transistor junctions. Now, another thing that this model shows us is where exactly the power is flowing from the left to the right side. So, of course, the 2 watts or amps that we put in will have to arrive at the other end. All 4 amps do go through the V1 current source, but what we can also observe is that about 3.5 amps are going through the heatsink, and everything else is going through the junction to ambient thermal resistances. So maybe this is not that useful information in this case, but could be important in other applications. Now, the main limiting factor in this sort of model is knowing the exact thermal resistances of each heat path. While the datasheets do provide some information, these values are usually extracted under some very specific test cases. For example, this heatsink will have a completely different thermal resistance if there is airflow around it, or on the other hand, if it's inside of a cramped box with a lot of other components. Regardless, having such a model is a good step forward, and if you're building it in a simulator, there are a few extra things that you could do with it. So the first thing to consider is that the input power for your thermal circuit does not have to be a constant. It can be the outcome of some sort of circuit bit. So for example, I have here this very basic transistor circuit to which I'm providing a variable supply voltage. And this means that the power dissipation is also variable. Now you can take this power dissipation equation and insert it into a thermal circuit where we have the ambient temperature and the thermal resistance. So here I use the behavioral current source to which I included the same definition. By doing this, you can determine how the junction temperature should vary in time, and then you can also take this value to another bit of circuit. So for example, you can measure it using a behavioral resistance definition and measure it using an ADC measurement. So this way you could create a complete thermal circuit. Now, unfortunately, you can't really take this dynamic temperature back into the transistors model. You can only define temperature as a constant. So right now it's set to 35 degrees Celsius. But what you could do is create an equivalent model for the semiconductors that would take temperature as a parameter. So this is a basic diode model that uses the previous junction temperature as an input. So here we can observe how the junction's forward voltage varies with the temperature input. Now, based on the available data and circuit complexity, more and more elaborate designs can be simulated in this way. Now, if you've ever performed a thermal measurement, you will know that temperature does not change instantly. Once you start up a circuit, here I'm measuring a power resistor using an NTC, you need to wait a certain amount of time for the steady state to actually be reached. This could be minutes or hours. So the temperature predictions that we get from the basic resistor models are only achieved at steady state. So the instantaneous temperature transfers that we have seen until now are not really the way in which a real-life circuit behaves. Now, if we look a bit more closely on the NTC measurement, we can notice that the curve has a familiar shape. It rises quickly, then it slowly stabilizes. This is the same type of shape you get with an RC circuit. And this leads us to how transient thermal models can be created. Now in practice, there are two common topologies used, the T and the pi networks, which are also known under multiple different names. In essence, these are RC networks that represent the various bits of the thermal interface combined to create a more realistic temperature profile. So here I just created a very basic model with generic values, but in reality all of these values will usually be different. So if we simulate the circuit and check the junction temperature for the three models, so the two RC models as well as a generic resistor only model, we can see that the steady state thermal behavior is exactly the same. However, the time element does bring an important feature into play. So if you dissipate a lot of power into a device, if this is done for a short enough amount of time, so here I have the two models with a pulse being applied to them. If we check the junction temperature for the two models, we can observe that if the pulse is applied for a short enough amount of time, the junction temperature for the steady state will be much higher than if we take into consideration the transient behavior. So the steady state power dissipation limit of a device, which is clearly defined in a datasheet, could potentially be exceeded if you're dissipating power for short periods of time. If the device doesn't have time to heat up, well, the limits will not be exceeded. So to illustrate this, what I have here is an old 2N3055 transistor stuck to a small heatsink. The combined thermal resistance from junction to ambient of the complete system is about 10 Kelvin per watt. So if I continuously dissipate 30 watts into this, the temperature of the junction would reach 300 degrees Celsius above ambient, which would clearly destroy the transistor. However, if I apply some specific pulses to it, nothing really happens. If the pulses are short, on the outside at least, there is barely an increase in temperature. Now, just to see what is actually happening inside, I cut the transistor open and applied a bit of paint to increase emissivity, and then redone the measurement. And this time, we can clearly see the pulses. The junction is heating up by at least 20 degrees Celsius during the pulse, but then the heat quickly dissipates. This could not be seen from the outside because of the large thermal mass of the casing, but the junction is still heating up, and potentially to extreme values. The topic of transient power dissipation is extremely important in the design of switching circuits, since here you almost never adhere to the steady-state power dissipation limits. During the switching transient, you are usually exceeding this value. Unfortunately, this cannot be measured from the outside, maybe only under some very special conditions, so the only practical way to determine the junction temperature is using a theoretical analysis. So the critical design question that needs to be answered is, will the junction of the transistor exceed its temperature rating or not during the transient? To highlight this difference, I first created a basic buck converter around the BCP53 transistor. So this is a PNP medium power transistor, which is rated for a continuous power dissipation of around 1 watt, according to the datasheet. But in this specific application, if we run the circuit, we can extract the power dissipation and observe that while the average is around 110 milliwatts, so well within the acceptable range, if we zoom in to the simulation results, we can observe that we are getting power dissipation peaks of around 10 watts. So is this peak power problematic or not? Well, the reason why I chose this specific transistor is because the manufacturer also provides a RC thermal model. So we can use this to figure out what the junction temperature will be during the transients. So just to make things a bit more clear, I built the equivalent circuit based on the model data from separate resistors and capacitors. And I also added in a 110 solder point to ambient thermal resistance. So this is approximately what you get with a 1 square centimeter of PCB pad. Anyway, to test everything out, I'm using a behavioral source for which the input is the power dissipated on the transistor. Now, I was getting some errors by using this specific formula, so the program didn't really like the IX terms. So that is why in the circuit, I added in these 1 milliohm resistors. So these are used to measure the current running through the branches of the transistor. Now, alternatively, you could use 0-volt voltage sources, but I went with this approach instead. Anyway, if we now check out our thermal transient model, and we look at the junction temperature, we can observe that while we are getting increases in temperature during the power dissipation pulses, it's not all that bad. So even if there are large amounts of power being dissipated, the thermal mass of the component is compensating for this, and the device is in absolutely no danger. And if we look over a longer period of time, we can see how the transistor is slowly heating up. Now, another interesting application is when the transistor is being used as a load switch. So especially if there's a capacitor on the output, when you turn on the switch, you will have a short period of high voltage differential as well as high current running through the switch. And well, if you multiply the two and extract the power dissipation, we are getting a peak of almost 90 watts when the capacitor is first turned on. Now, unlike the previous example, this is a single pulse, but it is lasting for almost half a millisecond, so it's quite long and quite large. If we check our thermal model again, so I left the same link between the behavioral current source and the transistor, we can first see that on the solder point, so on the outside of the transistor, there's nothing visible. So we go from 25 degrees to, well, 25 degrees. Nothing interesting is happening. However, if we check the junction of the transistor, we can observe that we are getting a huge spike. And this is taking the transistor over its breaking point. So we are reaching around 210 degrees Celsius, which is significantly above the 150 degrees rating of the component. Now, this was done at the ambient of 25 degrees, but if the ambient would be higher, the peak would also be worse. So this specific circuit, in real life, would destroy the transistor. But looking at it from the outside, you would never know that it even heated up. Now, while a transient model can be found as an external circuit, like we've seen with the previous component we looked at, this will not always be the only form of presentation. So, if we take the example of the BUK7K35, the manufacturer, under documentation, provides a thermal design model in a PDF form, so you can redraw this circuit in any simulation program you want, but it will still be separate from the transistor. You still need to provide a link between the transistor's power dissipation and the RC model. Now, the alternative to this is to have a complete model of both the transistor and the thermal circuit. So in this case, we also have an Electrothermal library for the BUK7 series. And this contains a library for a large number of transistors, but also you get an example circuit. So what we can see here is that we are getting a 5-terminal component. You have a single symbol containing both the transistor bit, so the gate, source, and drain, but also you have the thermal bit. There's a pin representing the junction temperature, as well as a pin representing the mounting point temperature. Now, this sort of model and package has two very important advantages. On the one hand, it's far more compact and easy to use. It's a single component instead of having two separate circuits. And the other big advantage is that, at least in this case, the transistor's operation takes into consideration the junction temperature. There's not just a power dissipation to junction temperature link, but also the other way around. Now, just to illustrate how this can be used and how it behaves, I made a few implementations. So you can either fix both the junction and solder point temperature to an external reference, so 25 degrees in this case. This will be more or less an ideal use case. You can set a specific mounting point temperature, so we just fixed this value. Or finally, you can provide a thermal resistance to the mounting board, and we'll connect through this to the ambient. Now, if we run the circuit, we can observe that the junction temperature in the three cases is different. So I set quite a high amount of power dissipation. That is why the temperature values are reaching such levels. But the point is that each circuit has its own thermal behavior. And the really interesting thing here is that even though the supply and the drive signal are the same in each case, if we check the three drain currents, these are all different. So this highlights that the transistor's behavior is taking into account the junction temperature. Now, for more information on this topic, the library also contains a proper application note describing how it all works. Having a thermal transient model of a transistor or other semiconductor device is not always the case. Not all manufacturers provide this sort of thing, and especially with older components, you're lucky if you even get an electrical model. However, a good datasheet will still have a few more useful data sprinkled around it. So if we have a bit of a look, other than the standard junction to ambient and junction to mounting point thermal resistances that represent the steady-state behavior, sometimes you will also get a transient thermal impedance graph. So this sort of graph illustrates an equivalent thermal resistance that can be used when the power dissipation pulse width and period is known. So you can either have periodic pulses with different duty cycles, or even the single shot is documented. So this will help in estimating the junction temperature for various transient times. Now, while this transient thermal impedance graph is not always provided, what is usually present, even in older datasheets, is the safe operating area graph. So this highlights the drain source voltage and drain current limits under DC conditions, as well as various pulse conditions. So these are usually single pulses, not repetitive, and the graph is only provided for 25 degrees. At higher temperatures, these limits will be shifted, but nevertheless, this should at least give you some sort of idea if you're overdriving the component or not. In the end, thermal design and verification is an integral part of electronic design. Both the steady state as well as the transient behavior, are important to consider, since each of these can come with their own problems. When simulation models are made available, this can easily be addressed in the circuit simulator, but even if these resources are not present, the datasheet will still usually contain a few clues to determine whether your design is reliable or not. And with that said, hope you enjoyed this video, and if so, there are more similar videos on my channel that you might want to check out. And if you want to be up to date with my latest releases, also consider subscribing. See you next time. Bye bye.